Well, thank you very much. So I guess this is one of 2 colloquium talks this week that will be about this topic. And I guess the idea is somehow an area in which there has been a lot of recent progress, and we're hoping for there to be even more progress in the future. And so, by the end of the talk, I want to tell you what we know and what we hope to understand about these torsion classes. There will be kind of torsion classes in the cohomology of certain arithmetic hyperbolic 3 manifolds. But before I get to talking about those, I just want to start by kind of an overview about the Langland's reciprocity conjectures, and then to give you a classical example, and then we'll talk about torsion classes in the cohomology of arithmetic hyperbolic 3 manifolds. But so the idea behind these is that there seems to be a connection, and in many cases it's known, between sort of very kind of different areas of math, say on one hand analysis or topology, and on the other hand number theory or arithmetic geometry. And the way that you can sort of make this connection explicit is that it seems that you can often match, say, spectral data, so systems of eigenvalues that arise from, say, the geometry or the analysis of certain highly symmetric manifolds. So this is on one side. And on the other side, you have arithmetic data. For example, something that could arise from counting solutions to Diophantine equations. So polynomial equations with, say, integral coefficients. I'll give you a concrete example of this. But before mentioning the concrete example, I want to say a bit about what these highly symmetric manifolds are. And they're always manifolds that come from group G over F. So the group will be basically any reductive group, so a general linear group. Even the case of GL1 is quite interesting. And F is going to be a number field, so some finite extension of the field of rational numbers. And whenever you have something like this, you can construct one of these highly symmetric spaces. So really, these are called locally symmetric spaces. And the way that you construct these, you take X to be the symmetric space for G. And this is essentially up to quotienting out by some torus in order to get finite volume. You look at the group of real points, and you quotient out by a maximal compact subgroup. And then to get the locally symmetric spaces, you further quotient these by certain congruent subgroups. So this space X has an action of G of R. And if you look at, say, gamma inside of G of Q, say, a congruent subgroup, arithmetic group, for example, something that's cut out from the z points by imposing congruence relations, you can form quotients x gamma. And as gamma varies, you have a tower of these. These are called locally symmetric spaces. And these, so their analysis or topology plays a key part on this side of the Langlands correspondence, which is often referred to as the automorphic side. And on the other side, what you have are sort of, you want to look at basically varieties defined by polynomials by polynomial equations with coefficients in f. And there's also, so on this side, there's also a hidden group that is G hat. This is the Langland's dual group of G. And so, for example, you could take G to be GLN or SLN, or maybe a symplectic group, SP2N. And this gives you G hat, GLN, PGLN, SO2N, plus 1. Yeah, sorry, I was right. So I decided to kind of start out by giving you this kind of vague outline and emphasizing the role that the group G plays, because in addition to this reciprocity principle that has to do with matching the two kinds of data that you see on the two different sides, on the, say, automorphic side and on the Galois side, sometimes the number theoretic side is called that. So in addition to this reciprocity principle, there's also a functoriality principle that has to do with how the spectral data, so the systems of eigenvalues for different groups, are related. And towards the end of the talk, when I want to say something about arithmetic hyperbolic 3 manifolds, I won't exactly use this, but somehow the idea is to make use of more than one group and to use the relationships between the different groups and exploit that in order to be able to say something. So that's kind of a common way to make progress in the field, by kind of playing around with different groups and trying to get the most out of it. And so I want to just give you 2 examples to keep in mind of these locally symmetric spaces. So if our group is SL2 over Q, then symmetric domain is SL2R over SO2R. And this can be endowed with a canonical complex structure, and then you identify it with the upper half complex plane. So the set, well, upper half complex plane, so you're looking at complex numbers with strictly positive imaginary part. So a priori, from the way that we've defined them as just quotients, double quotients of the group of real points, these just have the structure of a real manifold. But in this special case of SL2 over Q, you actually have a canonical natural complex structure. OK, so that's one. And then another example that's kind of, I don't know, you could say maybe you just go up 1 degree in terms of difficulty, still stay with SL2, but you look at SL2 over a quadratic field. And so F is going to be a quadratic field, and somehow the most interesting case, so where things look different, is the case where F is an imaginary quadratic field. So Q adjoined square root of minus D, where D is some positive integer, something like this. So Q adjoined I. And in this case, well, you can compute the dimension of the symmetric space for SL2 over F, and you're going to see that it's actually 3-dimensional as a real manifold. And in fact, it can be identified, so X can be identified with H3, so hyperbolic 3 space. And so in both these cases, these are just the symmetric spaces. To get the locally symmetric spaces, you have to take quotients of these. But here you have a complex structure, and when you take quotients, you end up with Riemann surfaces. Here, when you take the quotients, you get these so-called arithmetic hyperbolic 3 manifolds, but that don't have a complex structure. All right, so these are kind of the 2 examples, and I want to spend some time discussing what happens in the first case. And so, what kind of data do you see on the automorphic side, and what do you relate it to on the Galois side, and say a bit about the techniques that are involved in relating these things. So, right. So I'll just describe one example, but this is the case of SL2 over Q is one that we understand almost completely. So we still don't understand Moss forms. But everything else is pretty well understood in this setting. And so I'll just start out with one sort of system of eigenvalues that you can obtain on the automorphic side. And this is going to be given by an infinite product. So product, so Q times a product from 1 to infinity, 1 minus Q to the n squared, 1 minus Q to the 11n squared. And you can expand this out as a power series. It starts at 1, goes to infinity, an Q to the n, where you're going to get some integers an. And I claim, so I want you to think about the sequence of integers, and especially so the values AP, where P is a prime number, as a system of eigenvalues. So that's going to be something that shows up on one side, and you can just get it from this infinite product. Say if you want to compute what A7 is, you can. So it's pretty explicit. But what this infinite product really represents is a modular form. So explain in what sense this represents a modular form. So a modular form is a holomorphic function that lives on the symmetric space for SL2, and that has also many symmetries, and those symmetries are related to the congruent subgroups. So this is a holomorphic function on H satisfying many symmetries. And these are related to a congruent subgroup gamma. So with respect to some gamma. And also with a certain growth condition towards infinity. But one of the symmetries that our modular form satisfies is that it's invariant under sending, it's a holomorphic function of the variable z on the upper half plane, and it's invariant under sending z to z plus 1. And this means that you can write it in terms of a Fourier expansion and if you set Q to be e to the 2 pi I z, and you look at the Fourier expansion of f of z, it's going to be this infinite product. So that's what the infinite product represents. And somehow thinking about it in this more sophisticated way as the Fourier expansion of a modular form that lives on the upper half plane but has symmetries under this congruent subgroup, that's going to allow us to understand sort of the system of eigenvalues that it's carrying around better. And so this is related. I want to have two sides. So on one side, you have this infinite product. And on the other side, I said you want to look at Diophantine equations at varieties defined by polynomial equations with coefficients in Q. So in this particular case, on the other side, what you're going to see is an elliptic curve over the rational numbers. And so you can express this if you forget about, so an elliptic curve is a smooth projective curve of genus 1 together with a preferred point. And if you forget about that point, so you think that that's the point at infinity, you can express it via a cubic equation. And this modular form corresponds to the equation y squared plus y equals x cubed minus x squared. Okay. So that's what this is. And okay, I want to somehow count solutions. The idea is that for every, say, prime number p, you want to look at np, the number of solutions to the equation y squared plus y congruent to x cubed minus x squared modulo p. So we want to study congruence is modulo prime number. So you want to find the number of pairs x and y such that y squared plus y and x cubed minus x squared differ by multiples of p. And that's what this equation means. You think about this sort of modulo p. And if you count this, it turns out, so there's an explicit reciprocity law in this setting, which is you look at the pth Fourier coefficient of the modular form f, and it turns out that for any prime p, this recovers np minus, p minus np. So in general, you want to count the number of points of the elliptic curve, so you might have to do, this, you might increase this by 1, and then you would have p plus 1. But the explicit reciprocity law is this, where p is a prime number. And you can check this. So you can also count the number of pairs x and y, say modulo 7, and then you can check that indeed you get this relationship for A7. Okay, so that's an example of a reciprocity law that you encounter for SL2 over Q. And in order to sort of understand where it comes from, the first thing to do is to think about it slightly more sophisticated terms. And so the more sophisticated version of the reciprocity law is in terms of Galois representations. So the idea is that from both F and E, you can extract something called a Galois representation. So these are going to be two-dimensional representations of a certain group. This is going to be the absolute Galois group of Q. So this is a profinite group that you get by looking at the Galois groups of all the finite extensions of Q and then sort of taking an inverse limit of those. And so this is absolute Galois group. So you see all the symmetries of algebraic numbers. So numbers that are obtained as solutions to polynomial equations with rational coefficients. Absolute Galois group of Q. So it turns out both from the modular form and from the elliptic curve, it's possible to construct a two-dimensional vector space on which this large group of symmetries acts. And these are the Galois representations attached to both these objects. So these are both Galois representations. And so they're two-dimensional. It's a two-dimensional vector space over a field. This is the p-adic completion of Q. So just like by thinking about the rational numbers with the usual notion of absolute value, if you complete with respect to that, you get the field R. You can look at a notion of absolute value, that's the p-adic one, where two rational numbers are close, say if their difference is a multiple of p or of a high power of p. You can check that that satisfies the triangle inequality and does give you an absolute value. And if you complete with respect to that, you get this field QP. And it turns out, so both from the modular form and from the elliptic curve, you can extract these kinds of objects. And now really the key statement that is this reciprocity law is that these two Galois representations match. So they are isomorphic. And when people say this famous statement that all elliptic curves over Q are modular, what that refers to is the fact that you can match these Galois representations. And this is what Wiles proved as part of the proof of Fermat's last theorem using the Taylor-Wiles method. So the Taylor-Wiles method is exactly a way of showing that you can match the Galois representations for E and F. And this is a method that uses congruences modulo P or modulo P to the n. So somehow, if you think about what you're trying to match, the objects on this side, on the Galois side, sort of naturally live in families that are constructed by looking at congruences. And you can make the objects on this side as well also live in families, in p-adic families, by thinking about congruences on the side of modular forms. And somehow that is key to proving something like this. Instead of sort of matching these two objects, you make them live in families and you match the families together. And the second colloquium talk by Frank Caligari may actually say more about this side. So for my talk, I just want to briefly tell you how to obtain these Galois representations from the objects that we started with, sort of what goes into the construction of these, and then to see what happens if you try to do something like this in slightly more, in a more difficult case. So the first question you might ask is just how to construct these Galois representations. And so let's first think about how to construct the representation attached to the elliptic curve. So it turns out that that is kind of a simpler example of what you can do more generally. So the elliptic curve, and if you can think about it algebraically as being given by this cubic equation. But for example, if you look at you embed it into the complex numbers and think about the corresponding Riemann surface, then the elliptic curve is, well, it's genus 1. So it's going to be a complex torus of dimension 1 with a preferred point at infinity. So you can think about the elliptic curve over C, something like this. And another thing, so if you think about it this way, turns out the curve, this particular curve, has an extra structure, namely a group law. So you can make your preferred point the origin and then define what it means to add points on this elliptic curve. And it turns out, so you can sort of imagine this group law at the level of the Riemann surface. But the group law is actually defined over Q. So it's defined by polynomial equations with rational coefficients in x and y. And so if you look at the p to the n torsion points on your elliptic curve, then sort of if you think about it algebraically, what you have to do is solve certain equations, certain polynomial equations in x and y. So the coordinates of the points that are killed by multiplication by p to the n are going to be algebraic numbers. And because they're algebraic numbers, they're going to have an action of this huge group of symmetries, the absolute Galois group of Q. I'm just going to call this G sub Q. So that's one thing. So you can get an action of this group of symmetries on something that you extract from the elliptic curve. But if you think about it sort of from the point of view of topology, the p to the n torsion points are isomorphic to z mod p to the n z squared. So you're sort of putting this Galois action on z mod p to the n z squared. And then if you take an inverse limit with respect to n, you construct your two-dimensional Galois representation, the one that you're interested in. So rho e is just the representation on GQ of GQ acting on the inverse limit with respect to n of e p to the n. And this turns out to be GL2 of ZP, where ZP is the ring of integers in this p-adic field in QP. OK, so in the case of the elliptic curve, it's actually pretty explicit. But it turns out you can do this more generally. You don't need a curve that also has a group law in order to make this work. It turns out you can actually do this kind of thing whenever you have a variety that's defined by polynomial equations with rational coefficients. You can put an action of the absolute Galois group of Q sort of on the singular or Betti cohomology of that variety, as long as you extend your scalars. So I'm going to just make this remark and say that this is really a key ingredient in constructing our Galois representations. So if X over Q is an algebraic variety, then if you look at H star of the underlying complex manifold with rational coefficients, so H star, this could be Betti or singular cohomology, and you extend your scalars to QP, then it turns out there is an action of the absolute Galois group of Q on this vector space. And this is via et al. Cohomology, which was developed by Grothendieck. And it's somehow a cohomology theory for schemes that has some of the properties that Betti cohomology has for, say, complex manifolds. OK, so via et al. Cohomology. So now I should mention briefly how to construct rho f. And turns out, so you have to think a bit, well, you have to think actually more about the modular form and the space that it lives on. But ultimately, the source of this representation is the same as in the case of the elliptic curve. It is this et al. Cohomology of some algebraic curve that is defined over Q. So I'll just tell you how to get this curve. So f is this holomorphic function on the upper half plane, but it has symmetries. There's a precise formula, but I'm not going to write it down. But it has symmetries under a congruent subgroup gamma. So in this particular case, just to be explicit, this gamma is gamma 0, 11. So you get it by looking at matrices in SL2Z and imposing a congruence relation. So you want them to be congruent to upper triangular matrices modulo 11. OK. And the symmetries that F has are cooked up in such a way that F really gives rise to a holomorphic differential on the quotient. On H mod gamma. You can ask, OK, what do I mean by holomorphic differential? Well, so this has a natural complex structure, and it's possible to descend this complex structure to the quotient. And so this is a Riemann surface, in this case where you're working with SL2 over Q. So you can relate it, say, via Hodge theory. You can relate it to Betti cohomology. But somehow that's not quite good enough. You're looking for an algebraic variety defined over Q in order to be able to relate it to, say, arithmetic, to Galois representations. And so really the kind of miracle that happens here is that there exists an algebraic curve, y gamma. This is called a modular curve, defined over the rational numbers, such that you can identify this Riemann surface with the underlying Riemann surface, well, with the Riemann surface corresponding to y gamma over c. And then rho f is constructed from the étale cohomology of this curve, y gamma. So I will just so f is going to give rise to a holomorphic differential. Maybe I can call this omega f on this Riemann surface. And so I mentioned Hodge theory. So it is important to relate this differential to a class in H1 Betty. And so you can construct this, but along the way, you use also Hodge theory to kind of CF H1 Betty of y gamma underlying Riemann surface, and say even with complex coefficients. So that's something that shows up along the way, and it's a bit subtle because I didn't actually draw these spaces, these quotient spaces. I just said they're Riemann surfaces. So let me give you a picture. So you have the upper half plane, and on the upper half plane you have an action of the whole group SL2Z, because this is a subgroup of SL2R, and SL2R itself acts on the upper half plane. So when you want to construct a quotient, what you want to do first is find the fundamental domain for this group action. And so the fundamental domain for SL2Z is given by the following familiar picture. So this is 1, minus 1, and then 1/2, minus 1/2. And so somehow translation z goes to z plus 1 can be expressed in terms of the Möbius transformations given by SL2Z acting on the upper half plane, and also inversions about circles. So it turns out a fundamental domain looks something like this, and the corresponding quotient, H mod SL2Z, maybe looks something like this. So you have to identify this side with this side, and this one with this one. And you will get a couple of orbifold points. They're around roots of unity, so around I and cube root of unity. But otherwise, it looks just like a punctured Riemann sphere. And so what's important for us, that we can descend the complex structure to such a space, but also this is a non-compact Riemann surface. And so you have to use kind of a refinement of Hodge theory that deals with the fact that the surface is non-compact. But you can still relate your differential, which has a growth condition, towards this cusp. You can still relate it to a class in the Betty cohomology that you're interested in. And say, OK, our f is really a differential for a quotient h mod gamma. And so that would have a larger fundamental domain. The corresponding Riemann surface will be a cover of this. So maybe, h mod gamma looks something like this. And instead of having just one missing cusp, it could have, say, 3, something like this. OK, so these are some pictures. Right, so what I want to do for the rest of the talk is kind of explain what happens if you try to understand some of these things for the other case. So what if our group is now SL2 over F, where, for example, F is Q adjoint I. So an imaginary quadratic field. What changes? Well, you have your symmetric space, which is hyperbolic 3 space, can take quotients of this by congruent subgroups, and what you get are 3-dimensional hyperbolic manifolds are referred to as arithmetic hyperbolic 3 manifolds. I guess in this case, maybe they're called Bianchi manifolds. They were originally studied by Bianchi. And so just like we had our modular form F on the upper half plane, and we could relate it to the Betti cohomology of one of these locally symmetric spaces, in this case, one of the modular curves, you can also relate the Betti cohomology of these arithmetic hyperbolic 3 manifolds to so-called automorphic forms. So their Betti cohomology can be related by a refinement of Hodge theory. So it still works in this case to automorphic forms let's say I want to take this to be x sub gamma, and then the classes, well, you always have lots of symmetries, and you can always kind of think about systems of eigenvalues for those symmetries. But the classes that occur in the Betti cohomology, say with complex coefficients, like of one of these arithmetic hyperbolic 3 manifolds, can be related to automorphic forms. So you can think of these classes as analogs of our function f that we wrote down explicitly. Okay. However, something clearly breaks down. So you don't have any hope of having a complex structure on one of these spaces since they have an odd real dimension. So you have no way of having the structure of an algebraic variety, and then you don't have access to Étale cohomology, and you can't make the connection to Galois representations, to number theory. So you have sort of automorphic forms, and you think about them in terms of the Betti cohomology of these spaces, but you're sort of stuck trying to connect them. So there's no direct connection. In this case, so one clear problem is no direct connection to algebraic geometry. Okay, so it turns out you can still understand these classes. You can still make the connection, but it's somehow indirect. I'll explain what the idea is in a minute, but before that, there's another problem that shows up in this setting that, again, may be mentioned more in the colloquium talk on Friday. So, I mean, gave you a hint about how to construct the Galois representations, but I said sort of one thing that's really important. So the reciprocity law itself is given by being able to identify the two Galois representations coming from two different sides. And this relies on this congruence method, and so it really relies not on thinking about the cohomology with coefficients in a field of characteristic 0, but really with coefficients with torsion coefficients. So the second problem is that you need to understand, well, I could say h star of x gamma, say zp, or z mod p to the nz for any n. In order to, yeah?
When you're saying to identify these, do you mean to prove that they match or to define what it means to match?
To prove that they match. To define what it means to match, you can do it via this explicit relationship that I gave, like AP is P minus NP. So basically, you can say what traces do. But in order to prove that they match, you need to construct families on both sides and study the relative sizes of those families and kind of be able to identify them. So in order to do that, because the method is one that involves congruences, it just makes more sense. I mean, it's somehow you're forced to consider cohomology with coefficients in z mod p to the nz for any n. Right. So this is something that is made explicit in work of Caligari and Garrity that study the question of modularity beyond the Taylor-Wiles setting. So somehow in the case of SL2 over Q, you have to consider cohomology with torsion coefficients, but what you're working with is just a curve, and this doesn't actually have torsion. And so you just get the cohomology with FP coefficients just by reducing things from characteristic 0. And so in the kind of first example that we saw, and you can a priori argue that, okay, you need to work with congruences, but there's no actual torsion. Whereas here, there may be classes that don't actually lift to characteristic 0. And so this can contain a lot of torsion. And so the second problem in this setting is that somehow you need to understand not just the characteristic 0 things that are related to automorphic forms and that you can maybe attack with methods that are more analytic, but you also need to understand mod p classes that certainly can't be attacked by analytic methods. Okay, so these are, I would say, maybe two main issues. And one thing is that by understand, I mean, you really need to kind of construct Galois representations for torsion classes. And you need to understand those Galois representations very well. So have a lot of control over them in order to be able to plug them into the Taylor-Wiles machinery. So Galois representations for torsion classes. Okay, so this would be the sort of thing that you might have to say solving these problems would be preliminary to answering a question such as, I take an elliptic curve over this imaginary quadratic field. Can you prove that it's modular? Can you relate it to automorphic forms? Like, you need to at least have this kind of setup. And so I want to tell you about how to solve some of these problems. And so the solution to one comes from work of Harris, Lan, Taylor, and Thorne. Somehow they apply it to constructing Galois representations for these characteristic 0 classes. But somehow the solution for dealing with the fact that you don't have a direct connection to algebraic geometry, dealing with the fact that you have odd-dimensional real manifolds, that solution kind of can be applied to torsion, to characteristic 0, anything. So this, I think, is an idea maybe initially suggested by Clausel. And so somehow when we worked with SL2 over Q, in this picture, the fact that our Riemann surface, our quotient, was not compact was kind of a problem, because we wanted to understand some holomorphic differential and just turn it into Betty cohomology. And if this had been compact, it would have been just immediate to do this. And I said, OK, you need to be a bit more careful and take into account the growth condition and kind of refine things. So it turns out, OK, so this was a problem in this setting. But somehow the theory of compactifications of these locally symmetric spaces does actually offer a solution to the first problem. And so namely, I gave you these two examples. So a locally symmetric space X gamma can have an algebraic structure, say, arise from an algebraic variety defined over a number field, in which case we have our connection to Étale cohomology and to number theory. And in that case, X gamma is called a Shimura variety. or it could not somehow. Or X gamma could not have an algebraic structure. And I mentioned how there are all these different groups for which we expect reciprocity laws and for which we can study the corresponding locally symmetric space. So it turns out we know that for some groups, you do get a sort of more exact analog of what happens in the case of modular curves, in the sense that the locally symmetric space is a Shimura variety, and you can study it with more advanced methods that are sort of essentially along the lines of, well, what I described. And so, for instance, this happens for unitary groups. Somehow it's whenever you have an appropriate moduli interpretation of the symmetric space for the group as a sort of a moduli of Hodge structures of abelian varieties, you can do this. You can get an algebraic structure and study things the way I described. Symplectic groups. Moduli space of principally polarized abelian varieties is an example of one of these objects. And there are cases where you don't get it. And that's, say, GLN when n is greater than 2. Or, you know, SL2, but over an imaginary quadratic field. OK? But even if you don't have an algebraic structure, you always have a real manifold. And there is, there is a way of compactifying these spaces just as real manifolds with corners. And this is called the Borel-Serre compactification. So this is completely general. Whenever you have a locally symmetric space, you can construct a compactification that is a real manifold with corners. And that is so somehow homotopy equivalent to the space that you started with. So they have, if you look at their Betty homology, this space and this space, it's the same. And to give you an example of what this Borel-Serre compactification looks like for modular curves, so the standard compactification that maybe you've seen is adding just a cusp. That's not the one that I have in mind, so you can compactify it by adding a circle here. You can compactify this by adding circles where you would have otherwise added cusps. OK, so this is something that you can do generally. And the way that you do it is you keep adding sort of strata to this, just sort of to the boundary of the manifold until you get something compact that's a real manifold with corners. And the strata in the boundary are indexed by parabolic subgroups. Of the group G. So you start with some group G, and you look at a locally symmetric space, and then you understand how to compactify it, and you understand where the strata come from. And in this case, somehow this stratum corresponds to the Borel subgroup. So upper triangular matrices inside, say, SL2. Right. But you can do this in general. And then it turns out, so the really nice thing that happens is, say, GL2 over F is a Levy subgroup in a maximal parabolic subgroup of a certain unitary group, namely, so if you think about the group over R, the one that has signature 2,2. And for unitary groups, we have a very nice structure of algebraic variety. So we understand their Betty cohomology a lot better, even with torsion coefficients. So the torsion part is due to Scholze and is recent. But somehow this we understand really well. And then the thing that we're interested in, okay, I said SL2, but really GL2 is not much different. So the thing that we're interested in can be realized as sort of contributing to the boundary of this space that we understand much better. And so the idea is that you can use this in order to make progress on this. So maybe I want to be explicit. So you look at X gamma inside this compactification. This is a homotopy equivalence. You write down the excision long exact sequence for looking at this open manifold inside this real manifold with corners. So the excision long exact sequence tells you that essentially the difference between the cohomology, say I want to take Fp, but I could take Z mod P to the NZ coefficients as well, of our locally symmetric space X gamma. So you have, say, Hi to Hi X gamma with coefficients in Fp. And I could take here the compactification, or I could not, because they have the same cohomology. And then the difference is Hi of the boundary of X gamma Borel-Serre with Fp coefficients. And then this goes to Hi plus 1, compactly supported X gamma Fp. So somehow, up to some S1 bundles, say successive S1 bundles, the GLN or GL2 or SL2 over F classes that we're interested in will contribute to the boundary. And then you can chase them through, and either they come from compactly supported cohomology or from usual cohomology. And if you use Poincare duality, then by, say, you're interested in something here, it turns out that it's enough to understand the mod P Hi X gamma Fp, say, for every I. And now, so somehow the GL2 over F contributes here. And this is a U22 Shimura variety. So you have an algebraic structure, and you can work with étale cohomology and lots of other things. And so the other recent thing that's happened in the field that's been really spectacular is Schulz's theory of perfectoid spaces. And that has had applications precisely to understanding torsion classes in the cohomology of locally symmetric spaces, such as these arithmetic hyperbolic 3 manifolds. And using this kind of sequence, you reduce it to understanding torsion classes in the cohomology of Shimura varieties. And there, so these can be understood using Schulz's theory of perfectoid spaces. And that's what he did. And sort of using a kind of a p-adic version of Hodge theory. It's called p-adic Hodge theory. So somehow the theory of the Borel-Serre compactification gives you a solution to 1. And then if you do this, say, with mod P, or mod P to the n coefficients, and then you understand the classes in the cohomology of Shimura varieties well enough, then that also gives you a solution to problem 2. So it gives you sort of the necessary setup that you have for then trying to prove modularity lifting theorems in this setting. And maybe I just want to end with mentioning that there is one subtlety. So I mentioned that you want to understand, you want to kind of construct Galois representations, but also understand them very well, have a lot of control over what these Galois representations look like. And so the initial approach to constructing them that's due to Schulze does lose track of what these Galois representations look like sort of at the prime P. That's maybe sort of the most subtle information that the Galois representation carries within itself. And so you can construct it, but you don't understand it well enough to work with it in the setting of the Taylor-Wiles method. And so one maybe more recent idea that led us to kind of try and think about these questions more recently is sort of work in progress. It's joint with Peter Schulze that says, if you look at, say, X gamma, a unitary Shimura variety, and possibly with some restrictions, but I won't state the precise theorem. So restrictions maybe on sort of the field. Well, I'll just say some restrictions, and if you're curious, I can tell you more about what they are. But if you look at something like this, and you take D to be the dimension of X gamma, then you can show that HD of X gamma with FP coefficients and localized at a sort of generic enough, so nice enough system of eigenvalues, so you can show that something like this, maybe HI of this is non-zero only if the degree is greater than or equal to the middle dimension. And by Poincare duality, you also get HI compactly supported X gamma FP localized at something like this, not zero, implies I is less than or equal to D. So one potential obstruction, if you try to consider this excision long exact sequence, and you try to understand something from the boundary, is that a priori you don't know whether it comes from compactly supported or from usual cohomology. And if it comes from usual cohomology, I mean, it could be a torsion class that does not lift to characteristic zero. But if you put these two facts together, you can show that in degree D, HD of X gamma ZP localized at such an M is actually torsion-free. So everything is just the reduction of something from characteristic zero that we understand much better. And it surjects onto HD of the boundary of X gamma, say, again with CP coefficients and localized at M. So as a result of kind of having this more refined understanding of what degrees to expect usual in compactly supported cohomology in, you can understand a class in the boundary exactly as the, say, coming from some characteristic zero class that we do have a lot of control over. So I guess the hope is that maybe this can lead to genuinely understanding the Galois representations for the torsion classes in the cohomology of arithmetic hyperbolic three manifolds better, and then potentially to new modularity results in this setting. So I'll end here. Thank you.